To part 3 of the Introduction to Programming in Modern Fortran tutorial. I'm Daniel Price. I'm an Associate Professor of Astrophysics at Monash University in Melbourne, Australia. So we're on part 4 of this tutorial now. You can download this from my webpage, but we've gone through the basics of how to write a Fortran code, some of the basics of modern Fortran, and how to organize your code. And in particular, where we arrived at the end of the last tutorial was we wrote a basic makefile, which is here in my text editor, and we can simply compile our code by typing make, or we can type make clean to delete the temporary files. We type make to run our code. So our code is a very simple one. It's just calculating the area of a circle with this area function. All right, so I'm going to delve into some more details. And in particular, one of the details you need to understand straight away in Fortran, especially if you're solving mathematical equations, is the concept of the floating point precision and how you work with variables of different types. So Fortran has what you call strong typing, which means that every variable has a type explicitly defined. And what we mean by the type is basically in the computer, the number of the amount of memory that's used to store that variable. So by default, real and integer variables are stored with 4 bytes, which obviously gives you a limited amount of precision. So 8 bits to a byte. That gives you a limit on the kind of what's the highest integer you can represent in the computer, for example. And so the basic types of variable in Fortran, you can have integer with real, logical, and character. But there's an optional parameter at each of these, which is called the kind parameter. So for example, if we wanted to specify an 8-byte real instead of a 4-byte real, we could simply use kind equals 8 x. And x is different to r in this example because it has more precision. But you could drop the kind equals if you really want. You could just have real brackets 8x. And in old Fortran, you used to be able to type real star 8. Now, this is not exactly what you're supposed to do to specify the precision of your variable in Fortran. So technically, the kind parameter doesn't have to be the number of bytes of storage, but in every compiler that exists these days, it's either is the default or can be made the default. So it's perfectly safe to do that. But the way you're supposed to do it, I'll show you in a minute. And you're supposed to use this function called selected real kind. So essentially, you're supposed to tell Fortran what precision you require. And so I'm going to do that. I'm going to make another file here. So I'm just going to say touch precision.f90, and instead of just junking everything in my main program, I'm going to make a module, and then we're going to just make some calls to that module to see what's happening. So here's my new file called precision.f90. So remember, we start all Fortran modules with the word module, and end module precision, and we should always put the implicit none. And a good practice is also to use the keyword private as well. So that makes everything internal to the module by default. And so you will only make public the things that you intend to make public. All right, so I'm going to just write down what the purpose of this module is. I'm going to define the precision of real variables. And what do I mean by precision? Well, you'll see this in a minute, and we'll get to that. So, for example, we could define an integer parameter called dp, which is equal to 8. And then I could define real kind equals dp, my variable called x. But instead of letting this just be 8 by default, what Fortran wants you to do is do selected real kind, and then you tell it the precision you want. So it's the precision, I want like 10 digits, and I want up to the power of 30 in the exponent. And I can define that as my double precision parameter, and my single precision would be half of that. So single precision is selected, real kind, p equals 5, and r equals 15. So you're telling it what precision you require. The other way of defining your precision variables is to simply use... Now remember, in the first tutorial I told you that numbers have a type. So for example, typing 0 with a dot gives you a real number. Typing a 0 with no dot gives you an integer. Typing a 0 with a d0 on the end. So you can type numbers like 1.e to the 10. That's 10 to the power of 10 expressed as a real number. Yep, so 1e to the 10 is the way you would write 10 to the 10 as a real number. Well, actually, technically, it would need to be written like this if I was going to do it. So otherwise, 10 to the 10 like that would be an integer. So a real with the power like that will be like that, but you can simply write 1.e to the 10. And so there's a double precision version of that, which is 1d to the 10, which is 10 to the 10. And that's a double precision variable. So you could simply say that I want my double precision numbers to be the same kind as the number 0 in double precision. All right, so I'm going to show you what this means. So we're going to make these kinds public. So public is going to be my double precision, my single precision, and I'm going to make a routine called print kind info. So remember, we can have subroutines in my module. So I'm going to make a subroutine. I'm going to say what it does to print information about precision. Okay, so it's going to be called a subroutine. So a subroutine is exactly the same as a function. It just doesn't return anything from the doesn't have a value. So in C you would call it a void function. So a subroutine in Fortran is just a void function. So print kind info. Okay, so that's my basic shell. So I don't need implicit none here because I've already specified it at the top of the module. So I actually don't, so implicit none is implied in everything that's a part of the module. Okay, but I'm going to define some numbers here. So I'm going to call real single precision, pi single. I'm going to do real double precision, pi double. I'm going to print some information about these. So for example, double precision is kind equals, so you're going to see that my SP should come out as 4 from selecting this real kind according to the precision I wanted. And the single precision, sorry, that should be the single precision. And the double precision is the kind DP. And I'm going to print my DP alt. So I'm already using some bad practice here, which is I'm cutting and pasting, which you should not ever do when you're writing code. Kind of a double precision number is DP alt. All right, so let's leave it at that for the moment. Again, we've written probably too much code already, and we really should just make this code work. So just like before, I'm going to keep just the basic shell of my program. I'm now going to just delete this stuff because we don't need it anymore. So there's nothing in my program now except implicit none. I'm going to use this precision module. The only thing I'm going to use from my precision module is the the name of the subroutine, which is print kind info. So my program just simply consists of this single call, which is print kind info. And you can give brackets if you like. You don't need to give brackets, but it's up to you. Now, so I've got a new module called precision, and I'm going to use that module in my main code to print the information about the kind. So this is kind of programming in a more object-oriented way. So some of this information is public, but some of it's kind of private to the module. So in particular, unless I declare these things public, you would not be able to access these variables outside the module. So you can program in Fortran in a more object-oriented way if you wish to do so. All right, so what I need to do is add this to my make file. precision.f90, and I need to put it before maths.f90, so maths.f90 needs to depend on precision.o. All right, so we can simply type make. Okay, so we've got a problem, which is that precision.o had a couple of warnings about unused variables, but then it says can't open module file precision.mod, and that's because I called my module prec, and that means that is the name of the module there. So probably good practice would be actually to change the name of my module to match the name of my file, so then I don't get confused. So basically I couldn't find a module called precision because I'd called my module prec. All right, so let's type that again. So we've got an unused variable. So maybe good practice would just be to comment out those unused variables. So we're not going to use them just now, so we'll just comment them out with an exclamation mark. And so what I want to achieve is that my code always compiles with no warnings or errors. So I know my code is clean, I haven't made any mistakes, the compiler is trying to tell me as much as possible, and so when I trust that my code compiles without errors, it should be working. All right, so you can see what we hope to achieve here, which is the kind, it just prints out, these are integer variables. So I requested a double precision of a certain, a number which is of a real kind of a certain precision, and it gave me the number 8. So the kind 8 is going to give me that precision at minimum. And if I use a kind equals 4 real, then it's going to give me this precision at least. But the kind of a number which is types like 0.d0 is kind 8. So that's a real of kind 8. Now the kinds, again, they don't have to be the amount of bytes used for the storage, but in practice, that's nearly always what it is. So kind 8 means that the real is stored with 8 bytes of memory in the computer. All right, so why is this useful? So now we'll go back to adding our little extra variables. So you notice what I did there is I realized my program was getting too long, and I decided to test it just before adding too much more information. So that's the key thing, is don't try and write a lot of code. Just write a little bit of code, get it working, and then keep adding to it. Because now we know the code basically works, we can keep adding to it. All right, so let's define pi single. Now, I want to do 4 times a tan of 1, but I want my number 4 to be the same kind. So I'd have to type number 4 underscore sp, and that gives me the number 4 in the type, in the single precision data type. And the 1.0 would also have to be in single precision for everything to be consistent. And the same thing, a double precision would be double equals 4 underscore dp a10 underscore dp. All right, so we can simply now write, well, let's move this block of text up here. Let's print out some more information. So pi in single is pi underscore single, and print, sorry, I've gone off the end of the screen here. Print pi in double is pi underscore double. And what you should see is that I get more digits in the double precision case than in the single precision case. All right, so let's type make, no warnings, and we can run our program again. And you can see that this is exactly true. So pi in single precision gives us 3.14195926, and pi in double precision is 3.141592653589791. All right, but what would happen, for example, so if we just did the following in single precision and we didn't type our numbers correctly, but we then did implicitly what we're doing then is a type conversion on the left-hand side. So actually I'm going to do this twice. So I'm going to do it again here, and then print pi in double again. I'm going to do it up here, but without doing the underscore dp, just to show you what the impact of, why you need to be careful with the precision of numbers. All right, so I'll compile my code again and run it again. And what do we get? All right, so you can see what happens. So in single precision, we get 3.141599274. Pi in double precision done correctly gives me the correct value of pi, but in the one done incorrectly, I just get random digits off the end of my variable. And that's because the right-hand side of my equation, 4 times the atan of 1, has only been computed in single precision, and then I converted it to double precision on the left-hand side. So this is a bit of a mess. So what I've effectively done is I've made a type conversion which I didn't really know I was making, and that's simply because I didn't type my numbers correctly. All right, so that's what we've just been doing, but I'm gonna teach you a better way, which is simply to use the compiler to change the precision of your numbers. So my preferred approach is to simply, so that's the way that Fortran kind of wants you to do it, but that's not the approach I would recommend. So the approach I would recommend is simply to do something like the following. So declare pi equals 4 times atan of 1. Now then notice that I can declare pi here quite happily because I haven't conflicted with what I've imported from the module. And I'm going to print pi. Now, I haven't told it what type I want this real to be. And so my preferred approach is to, instead of trying to use these 8s and 4s all over the place, I'm just going to let everything be a default real variable. But then I'm going to use the compiler to change the type of the real variables. Okay, so let's type make. So I get pi is 3.14159.274. So then what we can do is use the tricky compiler flag. So there's a compiler flag, and it's different for each compiler, but the compiler flag in G-Fortran is fDefaultReal8, which tells me that I want the default real number to be an 8-byte real. Okay, so if we go look in our program, this is a default real, and I want to tell it that I want the default reals to be 8 bytes. And the advantage of this over what I just did in this precision module is that not only the variable on the left is upgraded, but also my numbers. So I can continue to type numbers like 4 dot and 1 dot, and those numbers will get upgraded. So this number here will be upgraded to double precision, and this number here will be upgraded to double precision as well. All right, so when I run my code, sorry, I need to make clean because I've changed the flags. And you notice I have this extra flag now when I'm compiling the code. And so now if I run this code, I get pi in double precision. And you can continue with this. So for example, if I wanted to make my variables 16-byte reals, I can just do make clean, make. Okay, so we do have to be careful here. Oh, so it's giving me a warning in the precision module because this is a 16-byte real, and I'm now downsampling it to a double precision real. So you notice that here, it's actually converted some of my real variables here, which is the ones that weren't defined with types. So those have been converted to 8-byte reals, but this thing on the left now, sorry, those have been converted to 16-byte reals, but the thing on the left is only an 8-byte real. Anyway, so we're not using the precision module at the moment. We can actually comment that out as well. So make, and we're running maths, and we get pi in to 16 bytes of precision. So we get a lot more decimal places. And if you trust me, or if you know the digits of pi off the top of your head, you can verify that those digits are indeed correct. So the recommended procedure is not to use, now again, your philosophy might differ, but my philosophy is not to use these, try to avoid specifying the kind of real variables in the program. Unless you really want something to be a limited precision. So if you want to limit the precision to, say, 4 bytes, or if you need to specify that it's 4 bytes because you want to write it to a binary file, and the binary file requires that it's 4 bytes. But if you just want your numbers to be consistent, and you're trying to just do maths, then I would leave your precision to just be real, and use the compiler flag like this fDefaultReal. 8 to specify that you want your reals to be 8-byte reals instead of 4-byte reals, so double precision numbers. All right, so there's an old Fortran way of doing this as well, is you could also specify double precision. This is the same as a real star 8, but again, the problem here is that we would need to specify these numbers in double precision as well, otherwise our value of pi will be wrong. So if we do that, we're going to get a 8-byte pi, but actually there's something tricky here, which is the default real clean. There we are, and maths, that still works. Why does that still work? I think because we need f default double. So we should take these variables off. Make clean. Make maths. You can see now that our pi has some garbage digits again because of this type conversion. So again, what you would need to be careful of is you could type the d0 and the d0 off the end of there, which means 4 to the power of 0 in double precision. Sorry, 4 times 10 to the power of 0 in double precision. And this is 1 times 10 to the power of 0 in double precision. But it all gets a bit messy. So my recommended procedure is you just simply use real parameter pi equals 4. Your numbers look like numbers. And just use the minus f default real 8. And if you want to keep your doubles as the same precision, you can keep f default double 8 as well. Otherwise, it will promote them to 16 bytes. Okay, so you can type make clean, make, and we get pi to 8 bytes of precision.